For my project, I wanted to analyze the process of heating up a bottle of milk for my daughter. And to do this, you have to heat up water and then place the bottle in the water to warm it up to avoid getting hot spots that you would get if you just put the bottle straight in the microwave. And these hot spots kill the nutrients and make it unhealthy for the baby. At first, I thought it would be a simple lump capacitance problem. We'd have the bottle in the water, it would receive heat from the water, and that would be the end of it. But upon further investigation, I found that it was not this simple. But first, let's go through the theory. The theory is that you'll have the hot water on the outside of the bottle. It will be heating at the outside edge of the bottle, causing it to rise up, and the cold milk in the middle will fall down, and it will create a circular motion in the bottle and cause it to heat up. Through this, you are able to keep a constant temperature, and it heats up and is healthy and preserves the nutrients. But upon further investigation, I found that you will have the water will lose heat to the bottle, but it will also be losing heat to the environment. And that made this problem a little bit more complex. So to start, we have a resistance network. We'll have the milk as one of our resistors. That will have the plastic bottle. Then you'll have the water, the glass measuring cup, and the air. And to model this, we also took the equations for transient conduction and we model them for the heat transfer going the direction from the water into the milk and the heat transfer going out of the measuring cup. And by doing a simple energy balance, we, with the help of Brother Daines, came up with these two equations. Then we did the experiment by putting a thermometer in the water, a thermometer in the milk, and then having a timestamp. And I videoed the process to heat up the milk. And when the milk hit 37 degrees, which is body temperature in Celsius, it is at the proper temperature for my daughter to drink it. And so we just watched the water cool down, the milk heat up, and then we could record the time. On this graph, we have our timestamps. Then we have our experiment. The milk starts at 10 degrees out of the fridge, and the water is 80 degrees out of the microwave, or off the stove, whichever you choose. And then the milk heats up, and the water cools down, as we predicted would happen. We can tell that our calculated model is a little off from our test, but when you look at the graph of the data, they follow very similar trend lines. You see that the water is cooling down and the milk is heating up. For fun, I decided to graph our model all the way out to equilibrium, which it meets here, and then it will become one solid lump capacitance, and we could treat it as just losing heat to the environment. One of the problems I ran into was when I was doing my calculated data, I didn't account that K was going to change with the temperature. And as I noticed that, I had straight line trends, and that wasn't accurate. So I had to go in and make an Excel sheet that was able to interpolate our thermal conductivity for the milk and the water as they change temperatures, because that had an impact on how fast they would transfer the heat into the bottle. And so instead of having a straight line, we're able to have this curve. We see that it transfers faster at the beginning, and then it slowly tapers off. As you can see here, as well, in our calculated theory, it will just slowly taper off until they meet the same temperature. That was my main struggle, And then another one I had was I wanted to see if different properties could heat up faster. And we find that when you use glass bottles, they're able to allow the heat to transfer into them faster, and the bottle can reach its temperature quicker. But overall, we see that the model that we made with the two equations, solving them with a timestamp simultaneously, that they follow very similar trends to what we saw when we actually tested it. And we can conclude that our model was good.